Hello all, my name is Ibrahim Sabit and I'll be doing a presentation of performance evaluation of different machine learning techniques for basically predicting heart disease. Referring to the report of World Health Organization, heart disease causes millions of global deaths per year, and some causes of heart disease are mental stress, work overload, and many other sources which the paper did not really talk about. The problem is that since heart disease diagnosis is made from a doctor, this can be time consuming and very expensive. So the solution is just to say, hey, let's not, use basically a doctor to diagnose our heart disease. Why not just create automatic medicinal system, which is basically going to use a workflow of classification approaches based on multiple machine learning methods for diagnosing heart disease. And basically, the goal is to evaluate each model in terms of performance measurements and see which model is better. The dataset consisted of 270 samples. Of the 270 samples, 150 samples were without heart disease and 120 samples were with heart disease. The positive class in this case is presence, and the negative class, they defined it as being absence. To predict heart disease, 13 parameters were used. For example, age, chest pain, resting blood pressure, and etc. Before the article went on to and discussed its results and findings, it conducted a correlation matrix, and they did this with each individual binary classifier. So, for example, they did a correlation matrix of just absence and wanted to see how the predictors correlate to absence. And as you can see, max heart rate has the highest negative correlation to absence, and sex is the other one of negative 0.18. If the parameters are not negative, they are all positive, but they all are very weak. They are not above 0.5. They did the same thing for presence. They created a correlation matrix for presence, and when you look at the correlation matrix, we can see that we have more negatively correlated values to presence, and that is sex, chest pain type, max heart rate, and angina, and TFR. But if a R value is not negative and it's positive, we can still see that the positive R values are still very small and they're not really strongly correlated to presence. So the models that were used were 6 supervised machine learning models in the classification of heart disease, and they are artificial neural networks, support vector machines, naive Bayes classifier, logistic regression, k-nearest neighbor, and classification trees. So before I wanted just to move on, I wanted to just to put a model into context of the SVM. And once again, the SVM is just trying to find the line that best separates the classes of presence and absence in my case, in this paper's case. And they're just basically just trying to achieve generalization by finding a line that is basically best separating the points, and it achieves that by maximizing the margin planes. So basically the goal of SVM in our context is just to find the optimum hyperplane, which is going to maximize the distance between the two binary classifiers, absence and presence. The same could be done for the other models, but due to time constraints, I won't be talking about them. So the article also was using a tenfold cross-validation in evaluation of the classification performance, and the classification models evaluated used 8 quality measures. And the measures are accuracy, sensitivity, specificity, precision, NPV, FP rate, and rate of misclassification, and F1 measure. Looking at this confusion matrix of each of the models, we can see that logistic regression has the highest number of true positive cases of 133. Artificial neural networks has a next highest of 131. And looking at the false positive cases, we can see that the classification tree has the highest number of identifying the false positives, and SVM has the next highest in the false negatives and identifying false negative cases. But looking at the true negatives, we can see that although logistic regression has a high number of true positives, it also has a high number of true negatives. But the model that has the highest number of true negatives is our SVM. The paper also delved into the performance measures using sensitivity, specificity, accuracy, and precision. And as you can see from this table, logistic regression has the highest number of classification accuracy of 0.85. The next model that had the highest is 0.84, which is very, very close to logistic regression. And SPM and actually NIBase was the other one with an accuracy of 0.83. But looking at logistic regression, we can see that it has a good number of sensitivity. It has the highest sensitivity compared to the other ones, and also it has a good number of precision. But SVM also has the highest number of precision of 0.9, and it has a high number of specificity of 0.89. The model that is lacking is the classification tree, and you will see further on that the classification tree lacks in many other aspects when you are comparing models. Looking at this other model performance measurements, we can see that, well, first to analyze the NPV. The NPV is just basically a ratio of the correctly predicted negative presence of heart disease to the total predicted negative total samples classified as the presence of heart disease. And so the model that had the highest NPV was 0.85. But the most interesting one is the FP rate, the false positive rate, and the misclassification rate of our MSC and the F1 score. As you can see from the false positive rates, SPM had the lowest number of false positive rate, which is good because you want to minimize that. The model that had the highest false positive rate is logistic regression of 0.27. And also, if you look at the RMSC of misclassification of points, we can see that logistic regression is actually having the highest number of misclassification of 0.23, and the KNN actually has the smallest number of misclassification points of 0.15. Looking at F1, KNN had the highest F1 score of 0.87. The second model that had the highest was artificial neural networks of 0.86. And logistic regression had the smallest number of F1 scores, which is 0.79. So overall, the models look pretty equivalent. There's not that much of a difference, but if you want to weigh one more than the other, looking at the misclassification rate and the F1 score and FP rate is really good. So one other interesting thing that the article did was use a performance evaluation called ROC of each predicted class. So for example, this is a predicted class of absence, right? So it's just basically just comparing the specificity against the sensitivity. And the model that is the best one here is SPM due to the fact that it's farther away from this line here. So we can say that SPM is the better one. SPM is the better one in predicting the absence of heart disease. And they basically did the same thing. They use a RC of specificity and sensitivity of the predicted class now of the presence. And from this, SVM is no longer the one that is predicting presence that well. We can now say that, the logistic rate regression is really good due to the fact that it's like more higher and more better, and it's closer to 1. The worst one, again, is classification tree. Even in the previous one, you can see that the classification tree is really not that good in predicting the absence. But in the presence case, the classification tree, again, once again failed in predicting the absent class to be like that good. But logistic regression seems to be a really good one. The key takeaways is that basically logistic regression had the highest number had the highest classification accuracy of 85%, with sensitivity being 89% and specificity being 81%. Some positives of the paper is that it had detailed performance measurements of models measured side by side, so you can really take a good look into seeing which models are better and how they react and compare to others. Some improvements that I suggest that the paper should have done is done some hyperparameter tuning and use grid search to find some optimal and best parameters, because this research used just default model parameters, and we don't know if like SVM or KNN could have been better in accuracy had you have better parameters for the models. And also the research should use more data samples and they should have maybe included a decision tree classifier in diagnosing heart disease. But yeah, that is all from me. Thank you so much. Bye bye.